Okay, so hi everyone. So I'm going to talk about Cisco ASA firewalls. So just a little bit about us, because it's been a work that I did with Aaron Adams. And we're part of EDG, which is the Exploit Development Group of NCC Group. And we do basically vulnerability research, reverse engineering, and exploit development. So a little bit of context first. If you don't know what an ASA firewall is, it's basically what you have at the bottom left. It's ASA stands for Adaptive Security Appliance, and it's basically full of features. It supports firewalling, VPN, gateway, router, and it's pretty amazing system. And you can have different sizes, but basically underneath it's the same software. Internally, an ASA, it's a Linux with a special ASA folder, which contains everything related to ASA. And it's a little bit different than iOS than Cisco IS in that Cisco IS is a proprietary operating system. Here we have a Linux base. They support both 32 and 64-bit devices. And the main binary is called Lina, and it's in ASA bin Lina, and it's basically a 40 meg binary that contains everything. It's kind of a critical device because it's the entry point for basically all companies' networks. And so basically, if you control an ASA device, then you can basically access to the VPN, you can access to the routing stuff, credentials, and you basically have access to all the internal network, and you can see everything that goes through the VPN. So it's a little bit scary if we think about it. But let's understand something. In 2016, last year, Intel released an exploit for a vulnerability, a heap overflow vulnerability in the Cisco ASA. They called their research "Execute My Packet." It was responsibly disclosed to Cisco before releasing it. Basically, the vulnerability they targeted is in the Cisco fragmentation payload. So it's something that is related to Cisco, like the name Cisco fragmentation. It's basically a payload specific to their need to do reassembly inside IKE itself. So the idea is you would send different fragments, and they're going to be all reassembled into a packet that's going to be interpreted as IKE. And there was a vulnerability in the way the reassembly worked. We're going to talk about it. I'm going to explain you what was the vulnerability. But basically, for now, we just need to know that there was a vulnerability in the way the packet was reassembled, and it was an integer overflow, and it resulted into a heap overflow. So what is really interesting about this vulnerability is it's pre-auth, so meaning IKE is used to establish a VPN, so the VPN is not established yet. So it's pre-auth, and IKE is available on the internet everywhere because it's used for the VPN. So they released their exploit in April 2016, and their exploit targeted IKE v2, a specific ASA version 924, and 32-bit only. It's pretty awesome research if you think about it, and they actually got the Pony Award of last year, so it was pretty cool. So what are we going to do from that? The thing is, exploiting a heap overflow requires understanding heap internals so we can abuse them. We actually understood their research and then reported their exploit to IKE v1 with different constraints, and also both for 32-bit and 64-bit and all ASA versions. But to do that, we had to understand heap internals. Also, we built 3 GDB plugins to analyze heaps and understand and basically abstract things so we could basically exploit bugs without just relying on memory dumps and without understanding anything. And it really assisted us into exploiting the bugs. So what I'm going to propose you to do is to participate to an awesome journey into ASA heap internals and flows. So we're going to focus our talk on 32-bit just for the sake of simplicity, but lots of concepts actually apply to 64-bit. Okay, so let's go. So what is Cisco fragmentation? So the idea is you have a fragment ID, which is going to be the same for all the fragments. And then you have a sequence number, which is different for each segment, each fragment. So you have sequence number 1, sequence number 2, and then one of the flag is to set the last fragment to 1, for example. What happens is the router knows it received all the fragments, and it can reassemble them now. Every time a fragment is received, it's going to be added to a queue, and when they are all received, it's reassembled. So you can have another fragment ID, then you can have sequence, you can have fragment with different sequence number. They can be in different orders, it doesn't really matter. Number 2, then 1, 3, and then at the end, when you get the last frag, you can reassemble your packets. Okay. So where is the vulnerability? The thing is, the way the fragments are received, each fragment will have a header and some data. And the header will tell basically the size of the data. And you will have the last frag bit also to indicate if it's the last fragment. But basically, because each fragment has a header, we don't care about the header because it's just metadata to say what the fragment is for. So when you receive a fragment, you add it to the queue, but the header is removed, so you basically subtract 8 to the length of the data. But the thing is, you can fake the actual fragment length. And basically, if you specify a length of 1 minus 8, it gives minus 7. So basically, the queue, it's going to be added a negative length, and you can decrease the actual length of the total length of the different fragments. So when you basically reassemble, when the packet is reassembled, the buffer that is going to be allocated is going to be less than the actual fragment data. And then basically when you copy the different fragments, you overflow into the buffer, and you can basically corrupt things on the heap. So what we try to achieve is quite hard, because basically we don't control the allocation or the free, but we can still gain code execution by corrupting things and by making the right request at the right time. But for now, I haven't explained how. So we actually need to understand the heaps, because we're going to corrupt things on the heap, but we want to get code execution right. So at the moment, like one of my colleagues, Chris Hanley, would say, it's a little bit like if we're trying to pick a lock through an industrial fan in the dark and with a paperclip. So we basically need some tool, right? Because it's really hard otherwise. So our talk is going to be about understanding ASA heaps, understanding Cisco ASA modifications that actually made it worse, and then in the process of the presentation, I'm going to show you some tool that we've developed that helped us exploiting the bugs. Okay, let's go through what is a heap. So I'm going to talk about 3 well-known heap allocators that are of interest here. We have dimalloc, which is the Dogley allocator, which is quite old, 1993. And then we have ptmalloc, which is the pair-thread allocator, which is these three heap allocators I'm going to talk about are really related because they are forked from each other. So we had dimalloc. Ptmalloc is a fork of dimalloc. So they share things. But basically, ptmalloc was developed in order to support multi-threading in a better way. The heap allocator would support multi-threading and avoid lock contention. And then we have the GNU libc heap allocator, which is probably the most famous because it's used everywhere on Linux and is used a lot on all the systems that are based on Linux. So heap manager usually assists us in allocating and freeing chunks. So if we want to get some memory to do some stuff, we're going to ask the heap allocator to do that for us. So it provides the APIs malloc and free usually. So usually it has some kind of region that the heap allocator controls and know it can use for allocating stuff. And basically when we do a malloc, we're going to basically get some part of this region that's going to be given to us so we can do whatever we want. And when we don't want it anymore, we call free and the heap allocator knows it can retrieve it for another use. So we allocate stuff, and basically the heap allocator, there are two strategies. It could either track allocated chunks. There are actually three strategies. It could track free chunk, allocated chunk, or both. But for performance reasons, usually the heap allocator only track free chunks. Because if it tracks free chunks, when you do a malloc, it knows the free chunks, so it's going to basically take one of them, give it to you, remove it from the list, and then last time you call free, it's going to take it back and put it back in the free chunk. It doesn't really need to track allocated chunks, and obviously, because malloc and free are called lots, it's for performance reason. So let's say we want to allocate something. It takes a free chunk, it becomes an allocated chunk, and so on. So I've talked about chunks. A chunk is a memory part that is basically returned by the heap allocator for us to use. We call it chunk. And what is really important about the three heap allocators I've been talking about is that they store the metadata for the chunk before the chunk. So when you basically have a heap overflow, so for example, if the chunk on the left, we can corrupt memory, we're going to basically corrupt some memory of the following chunk and basically corrupt some metadata on the heap. So that's why we need to understand how the heap works, because we're going to be able to corrupt things on the heap. The last term we use is bin. So the bin is basically a way to track free chunk. We have bin of different size. So if, for example, you want to allocate a 100 byte chunk, it's going to look at the bin for 100 byte chunks and just take one of them. It's easier for the heap allocator to return you a chunk if you sort the chunks by bin. And the last thing that is important is they are all open source. So if you actually want to understand what a heap allocator is, it's more complex than I'm not going to explain everything in one talk. But basically, if you look at the source, it's the best way, in my opinion, to get used to what a heap allocator is. Okay, so now we have these three heap allocators. We want to know what is used on Cisco ASA. They are based on Linux, so probably one of the three. We're going to focus on 32-bit, and we actually, if you reverse engineer the liner binary, you will realize that it uses a version of dimalloc, which is compiled directly into the ELF, rather than an external glibc, so that's quite interesting. And it does link with glibc, but it doesn't use the malloc function from glibc. So if we look at the disassembly, even if you're not familiar with x86, you can see strings that are used next p news p. And if you look at the source code, you can directly see that you have this kind of string. So you can say, oh, okay, they are using dimalloc inside the binary. And actually, if you look at more strings and you try to find more that are in the actual dimalloc source code, you can find, for example, this one and another one. You realize that if you actually look for these two, you can actually determine the exact version of dimalloc embedded into the binary, because it's the only one that has these two is 2.8.3. So it's actually it's a very nice step to understand that it's version 2.8.3, because you have some mitigations that are added over time in dimalloc. So for example, we know that this specific dimalloc versions doesn't have safe unlinking, which is a mitigation to deal with memory corruption on the heap metadata, because it's only enabled after 2.8.5. So it's good to know. Okay, so more concept about dimalloc 2.8, because now we know it's dimalloc 2.8. We have this concept of mstate and mspace. Mstate and mspace, it's basically the memory region I was talking about that the heap allocator need to deal with. And an mstate actually can contain several segments. It's just a way for them to say, okay, if we want to have several segments allocated in different places, they are going to be managed by the same mspace. So I'm going to use mstate instead of mspace and vice versa. They are very close concepts, so that's why. But basically, when you allocate things, it's going to be allocated in one segment or another. We don't really care, but what is important is if you actually know how the heap allocator works, then you can basically build tools to part the memory and give you a representation so you can interpret stuff in an easy way. So for example, first thing we wanted is to be able to parse an M state. Because basically it helps us, for example, to, okay, here we have the bin. Okay. So here we have the bin. So the bin, for each size, we have a list, a doubly linked list that's going to list us all the chunks of a specific size. So if we allocate stuff, we want to find our chunks, we're going to find them here. And then we have this maps that basically indicates how many chunks there are in the, or if they indicate basically if a chunk is, if a specific bin is empty. So if you have 1, it means it's not empty, and if you have 0, it means it's an empty bin. And then you have other interesting concept is, for example, this magic. We're going to talk about it. It's like a global cookie that is used for some kind of security, which is helpful. And then we have DV, which stands for designated victim. Basically, when you free a chunk, the latest chunk, it's going to be pointed by the DV. The idea is, usually when you allocate stuff and free stuff, it's going to be always the same kind of size. So it's an optimization to say if you free something and then reallocate it, it's going to basically access the DV and it knows the DV size, so it can know if it's going to reuse it. It's actually something that we want to exploit in terms of exploitation, because usually we rely on freeing things and then having a hole before stuff and corrupting this. So if you can access DV, it's helpful for us because we can check our exploit is actually on the right path. And you have the segment, which basically indicates where in memory are our data. So it's easy to determine the address of the M state because it's passed to M space malloc. So let's talk about that. So they introduced this term as M space. The idea is, before it was called an M state, but it was because the heap allocator would manage the heap on its own. But what you can do with the new dmalloc is you can manage your own M space, which is like an M state, but you can manage it. And you can have several M space, and you're going to pass the M space to the M space malloc function, and you can allocate things on different M spaces. So you define M space, and instead of calling malloc, you're going to call M space malloc and pass the M space at the function. So you create your M space, and the idea is the allocator maps a memory segment and store the M state into the first chunk of the M space. So this is how it looks like when you call M space malloc. So you have your M space, you have your segment inside the M space, and the M state structure that we saw earlier, which is just here to track things, is basically in the first segment. It's not really useful from an exploitation point of view, but it's useful to know where to find things because we want to build tools to analyze the heap. Okay. So theoretically, you can still use the malloc and the free. So you can have your own M space and still use and call your M space malloc, and you can still call the malloc function that's going to be handled by the heap allocator itself. But you can also choose to not use the malloc. So basically you define only M spaces, and then you won't have the malloc functions anymore. That's actually what we have in ASA. So if you actually look at and disassemble firmware, you look at malloc calls, and underneath it's actually calling several wrappers. But at the end, it calls M space malloc, and you can match that the function. You don't have the symbols and everything, but you can match this function M space malloc has all the dmalloc debugging strings, and it matches with the actual source code of dmalloc. So you have basically a wrapper that calls their M space malloc. So they base their implementation on dmalloc, and they don't use real malloc. So they basically use M spaces and only M spaces. and is statically compiled into liner. Okay, so the last concept we need to understand is the concept of mempools. It's something specific to Cisco ASA that they added on top of dimalloc. The idea is they want to track different M states, and they use this term, which is mempools. So mempools is like a region of memory dedicated to allocations for Cisco ASA components. So we built this tool, which basically show a structure, which is the mempool list, which contains different mempools, and each mempool will point to a M state, which a different name. So we have the one for DMA-related allocations, and the most important one, which is the general purpose allocation. So the M state we saw earlier is actually tracked from a mempool. So if we actually look more in detail the different wrappers, why they use wrappers and what they actually do with that, we're going to explain that basically rest manager calloc doesn't do much except dispatching to the next wrapper. And then mh calloc will actually add different things to the metadata. It will basically inject booking structures into the allocation. So if you reverse engineer it, you realize that it's calling mspace-malloc, which is what we told earlier, and ebx is the length, and it's going to add 24 before calling malloc. So basically, it's asking malloc to allocate more than the actual requests that was made from the user perspective. So why does it do that? Actually, it's adding another header inside, because we said earlier that dimalloc has its own metadata, but mempool actually Cisco adds another layer. So after the allocation, we can see that it's storing the length, it's storing a magic, and it's storing a magic at the end, ebx being the size. So at the beginning, it's storing the magic, which is quite funny because they use alloc A11C, alloc 123, and alloc CDEF. Pretty cool when you look at them. And then another interesting thing is they actually store the color of malloc. So basically here they retrieve the stack pointer, well, the base pointer, but it points to the stack. And basically they use that to find the address, the return address from malloc in order to store the return address, which is basically the caller of the function malloc. So if we actually, now that we've done the reverse engineering part, we're going to build the actual header that is specific to Cisco. This is a structure like this. You have a magic, which is always the same. You have the length of the data without this header and the dimalloc header, and you have two pointers that points to another allocated chunk, and then you have alloc PC, which is the address of the caller. So easy now we can build a tool to see what a chunk looks like. So if we look at a specific chunk and specify -v to specify that we want to see verbosity for the chunk, we see this is the dimalloc chunk, so it's going to contain a footer and the size of the chunk. And then we have the Cisco specific header, which contains the magic we saw earlier, the length, and this doubly linked list pointers, and then the alloc PC. So here, for example, we can see that the color of this chunk is ikey add receive frag. It's pretty cool because it means we can actually track who allocated what chunks. So that's something it's not possible to do it with dimalloc only, but with their addition, from our perspective, it's pretty useful. And then if we don't specify -v for our chunk, we can just print like a simple representation of the chunk. So the way we chose to represent things is we print the address, then M for malloc chunk or F for free chunk, then the size, then the flag that corresponds to if it's current in use, previous in use, And then the alloc PC, because we found it's pretty cool to know the alloc PC, so we just decided to print it as well, but we didn't print other stuff in the simple representation. And here, for example, for this chunk, if we take the forward pointer, which is mhfdlink, -8 to point to the dlmalloc header, and we print it, we can see that it's still something valid, and it's another chunk that was allocated from ikey. So it means our tool is working. Here we have another example where, yeah, that's the same chunk as here, but with detailed information, just for the completeness. So if we take, yeah, that's just what I said. Okay, so if you look at actually the Cisco shell, you can see that there is a command which is show memdetail, which basically allow you to print information about allocated chunks and free chunks. And this is a hint that something is going on under the hood, because usually a heap allocator will only track free chunks, so it wouldn't know how many chunks were allocated. But because they added a specific header, they are able to track free and allocated chunks. Just interesting. Another interesting thing is when a chunk is freed, there is no safe unlinking. And meaning that even though the dlmalloc would have safe unlinking, their mempool header doesn't have safe unlinking. Even though I said earlier that anyway, the version 2.8.3 doesn't have safe unlinking anyway. It's actually interesting to see that it evolved and the recent version now has safe unlinking, but the mempool still has the mempool still doesn't have safe unlinking. So anyway, the fact that it doesn't have safe unlinking is used by the Exodus Intel IKV2 exploit to get mirror writes. And another interesting thing about these mempool structures is that if you have a memory revolution bug where you can leak data from the heap, you can actually get some really useful information, because you have the pointers for the double linked list, which basically leak pointers to the heap, and you have these pointers to the text section, which is a function pointer, and basically you leak that an address from the text. So it can be useful to bypass ASLR. Okay, so we know they use dlmalloc. We know they use this mspace only way, but actually one interesting thing is dlmalloc has security features, and it shouldn't be that easy to exploit. But we're going to see that actually Cisco ASA modified the code and actually made it worse. So this is the dlmalloc header, which is before the Cisco mempool header. So it has a preffoot, the size, which is called head, and then for free chunk you have these free pointers. But what is interesting is usually heap managers reuse the first field for as a spillover when the chunk is allocated, because if the chunk is allocated, well, usually this field will hold the size of the previous chunk. But if the chunk is allocated, you can reuse that and basically pad and use that as a spillover. So it's really handy for heap allocator because it can save space and simplifies alignment. But for the newest version of dlmalloc, basically if you define footers, instead of using this part of memory as a spillover, when you create an inus chunk, it will basically store into the pref foot of the adjacent chunk some specific magic as a security measure. So it's not called pref size anymore, like previous size, but it's like a global cookie, which the purpose is if you corrupt the adjacent chunk, you don't know the cookie, so it's going to break and the heap allocator is going to abort or assert. Well, actually, if you look at the source code of dlmalloc, it says this check words are the same within each execution of program using malloc, but differs across execution. So externally crafted fake chunks cannot be freed. So that's exactly what I said. If you have a chunk before another chunk, if you corrupt the preffoot, you don't know in advance what the cookie is, you're not going to be able to do anything. So how does it work? Preffoot is calculated when the chunk is allocated. So if you have the address of the M state M, P the pointer to the in-use chunk, and S the size of the chunk, it's going to basically take the P the chunk plus the size to point to the next previous chunk, take the preffoot field and set it to the address of the M state XOR this magic. And this magic is like a global magic. So we can see that the security relies on the inability to predict both M and the magic. If you look at the source code of dimalloc again, M-param magic is initialized by a certain function called init-params, and it uses either a devu random to read the number of bytes to set this value to a random value, or call time zero. Okay, so it's secure. Then you need to have additional checks when the chunk is handled to check that the cookie is correct, right? So the thing that is done is when you free a chunk, it's going to take the address of the chunk, make it point to before the dimalloc chunk, get the M state for this chunk, and then check the magic from the M state. So how does it work? Get M state 4 is actually taking the chunk plus the size to access the preffoot field of the adjacent chunk, XOR that with a global, and it's basically the reverse operation as when we set it at the beginning. So we are supposed to get an M state address, and then once we have this M state address, we basically just access the magic, and it should be the same as our global. If we don't get that, it means something went wrong. So it's an interesting mechanism in that if we define M spaces and footers, we have this global cookie. So how is it implemented into ASA? The first thing we can notice is they don't use dev random, because if you reverse engineer the function, you're going to call that the create M space with base. You're going to see that there is a call to time 0. So it uses time 0 instead of copying a random cookie from devu random. The other thing that is interesting is because for some reason it's called really early at boot, wrap time 0 actually return a static value, which is this value. And this corresponds to an NTP timestamp, which is the new epoch. But what is interesting is it's constant. So what can we do with that? We call write time. It returns a constant. And then we see a bunch of operation XOR with 555, which is basically these 3 operations. So time 0 is constant. XOR constant, it gives us a constant. So you can actually confirm that with our tool, because the DLM state, so I didn't show the whole structure, it's like the big structure, but the magic that is stored is always the same. It doesn't change, which makes sense. Now we know why. And if you actually do the operation to set a preffoot into a chunk, M space XOR the magic, if you take, for example, this M space value, XOR this, it gives you this magic. And we could see that in our chunks, the preffoot is always set to this. Is it? It still relies on the M state address, right? We still need to know the M state address. Well, on an ASA 5505, where there is no ASLR, we only observe 2 different addresses for the main M state. So it meaning we have 2 different addresses and we have 2 different values, right? But it's still non-ideal from an exploitation point of view, because we still need to override this preffoot field, and if we don't know it in advance, it's really hard. Well, it turns out there is another customization Cisco made, which actually makes it all irrelevant anyway. So what did they do? If you look at dimalloc 283, you have this mspace free function, which if footer is defined, like I said, it's gonna get the mstate and then check the magic. But if you look at Cisco implementation, what they did is they're checking if the mspace is non-null, and if they're non-null, they basically trust the mspace, and they don't try to get the mspace from the chunk itself. Meaning, when they check the magic, since they trust the mstate, the mspace, it's going to accept the magic from the mspace, and it's going to be valid all the time, right? So, and the thing is, all the functions actually internally use mspace with a mspace non-null. So it assumes it's correct mspace, doesn't rely on using the pointers derived from the footer, and we don't even have to guess the footer at all. So, interestingly, you can confirm that by using their ikey exploit that they released, because they use a static preffoot that when you decode it, it gives an mspace address at this C8 address. But in our case, we didn't have an mspace at this address. We only encountered two different addresses. But if you try their exploits on your ASA, it still worked, because they don't check the actual magic. So for Cisco SKUs, it's quite hard to implement like a device which handles 1 million of packets every day or more. So basically, they try to do something performant, right? And so they don't want to do extra check where there is no need to. Well, in terms of security, we can see that it actually allowed us to override chunks and corrupt things because there is no check. So what is this good for? Well, let's use our tools to rule them all. So one thing we can do with our tool is we can send different chunks of the same size, and we can count where they end up being stored. So we see, for example, that the small bin for C0 chunks is empty. Then we send packets of specific fragment of specific size. For example, we send lots of fragments of the same size, 78 bytes IKV1 fragments, which end up being allocated into C0 byte chunks. And then we can see that our chunks are allocated into this bin. For example, if we take the first one and we use DL chunk to print the information, we can see that it's been allocated by the ikey stack. And here we can even see that it's been freed afterwards because it has the F flag and it's been freed by an ikey free all frags function. So we know it comes from our feng shui. So the next thing we can do is we want to line the heap layout, because it's cool to know it's our chunk, they are the good size, but we want them to be adjacent because we want to corrupt something that we control. So for example, if we print with -c as count 10 chunks, we're going to print 10 chunks, and we can see that they're all from ikey receiver process data, which is pointing to our data. And we can see that there are some free chunks in between. So we're going to see why. So we can see that we have some allocated chunks and some free chunks. So it gives us some kind of abstraction. If we get a little bit more detail, here we are analyzing a free chunk. So this free chunk, that's cool. It's been free by ikey. But actually, if we show the detail of the chunk with -vil for verbose and -x for hex dump, we can see that it has metadata, which is the dimalloc plus the mempool header. And then the data actually contain the bytes we send, the 42, because we send that payload in our example. So we know for sure it's our data. right? Because we're sending something to the router, we want to know where it ends up being stored. Another example with allocated chunks. Same thing. But here we know it's been allocated here, and it contains our data. So we want to exploit the designated victim scenario. For example, here, we show the DLM state with a designated victim. It's the latest chunk that has been freed by the heap allocator. So in this case, we can see that it's an 80-byte chunk. And what is really cool is if you have your debugger attached and you see after you're sending some stuff what is the designated victim, then you can basically send a packet of this specific size that end up being allocated in a specific size, and you know it's going to replace this chunk because this chunk is going to be taken. So you can exploit this. So the other interesting thing is we want to be able to analyze allocated chunks. So we saw earlier we are able to track free chunks, but here we are able to track allocated chunks using the mempools, the Cisco mempools. So in this example, we can see that the small bin, which contains the C0 byte chunks, is here. And we can actually find all our chunks in this bin, and we can see that it corresponds to the allocations we made. Okay. So now let's say we don't know where our chunks are, but we want to find it in an easy way without having to parse the structure by hand, because it's okay to find your bin and then find your chunk and do it by hand. But actually we have everything we need now to actually do it automatically. We can just call our new command mb binwalk, specifying the string data that not the string, the data that we want to look for, and specify just print me 5 chunks, and I want you to look for chunk of the specific size, and it's going to basically print us all the chunks that contain our pattern. And for example, here in this example, if we take this chunk, it does contain the 4141. Okay, so now basically we want to be able to craft the heap in a deterministic way. We are able to print chunks. So we set a breakpoint on the function where we know our interesting chunks for IKEA are allocated. And we use our tool to just print the chunk data. And here we can see all the so we send a bunch of chunks and a bunch of fragments that end up being allocated in chunks. And we see here the addresses are random. But at some point, it's beginning to be adjacent. So we use our tool to say, okay, that's cool. Now we can allocate chunks in a deterministic way, and all our future chunks are going to be allocated in an adjacent way. Oops, sorry. So the other thing is, we talked about reassembly. We can send different fragments. They are going to be reassembled, and we can exploit this. Why? Because if you send different fragments, they are allocated somewhere, then you trigger reassembly, and we don't need the fragment anymore because now we are going to deal with the actual reassemble packet. So the previous fragments are going to be freed. So we can basically control allocation and free as well. So for example, here, we want to see what happens when we send 3 fragments. So we saw, in this case, we basically set a breakpoint on malloc to see all the allocations. And we see that there are a bunch of allocations that go on the way. So we see allocations for one fragment, allocation for another fragment, allocation for the third fragment. And just using this, we can actually guess by the name what they are used for. So you actually have some structures to track the actual packets And then you have for the first fragment, a structure to track the queue, because the queue is empty for now. So we have this fragment queue, and then the queue entry to point to the packet. And then for the other one, you have the same kind of structure to track the packet. But then we don't need a fragment queue anymore because the queue is already created. But we just need to create an entry for adding the element to the queue. And same thing for the third packet. The only difference is for the third packet, because it's the last frag bit set, we're going to trigger reassembly. So our IKeyGetAssembled packet function is going to be called to trigger reassembly. So just setting a breakpoint on malloc, we can see that there are some allocations, and we know exactly what it's doing without having to reverse engineer everything. So the other thing we want is basically, we want to be able to control what we corrupt. So let's take a scenario. We want basically to allocate chunks in 2 different sessions. The idea is, if we control 2 different sessions, we can free one of them but not the other, and create some kind of holes before the other, which we control still, and then use this second one to do stuff. So we're going to use 2 sessions with fragments for both. So we're going to send fragments one after the other. We know we can have this adjacency because we saw it earlier. So we're going to craft our mind, do some brainstorming, and think we can maybe do that. Send fragment 1 from session 1, fragment 1 from session 2, fragment 2 from session 1, fragment 2 from session 2, etc. And the idea is then at some point we send the last frag for the second session, and we're going to create holes. And actually, if we do that, and we actually then look at the memory, we can see that we have MF. So we can see that we have exactly what we wanted. We have our session 1 still here, and we have holes for us to put stuff in, basically. So now what we can do is trigger reassembly for a specific size, and it will end up reusing a hole because the size is correct. In this case, we can see that it's actually reusing a part of the hole and still leaving a hole afterwards. So now we want to do better, because we want to corrupt more memory, to corrupt more chunks, and get more data corrupted, and more arbitrary write, and more mirror write, sorry. So what we want, basically, is to send fragment for session 1 to fill all the holes, then a different fragment in different sessions. The idea is we can arbitrarily free session 2 by sending the last frag. It's going to free the fragments. So we're going to trigger reassembly into this hole. And then when we corrupt a lot of memory, we're going to corrupt fragment from different session. And basically now we are corrupting the metadata for all the chunks. And because we control this session, we can basically arbitrarily free each one and get different mirror writes one at a time. But we want to use our tool to check it works. So basically, we do that. We send our fragment, and we trigger reassembly, and we can see here that our allocated buffer is before a free chunk, so 1C0 plus 40, which gives us 200. And we can see that it's before 3 chunks, each one corresponding to a different session, because we, on purpose, send different data in there just to see them in action. So it works. So here it's a different view where basically we have our allocated chunk before the free chunk and before our control chunk. So here I just annotated the different data for our chunk so we can follow. And then we can basically overflow the chunk. So by overflowing, the interesting thing is we overflow the size and we change it to a larger size. So what ends up being changed is the 40 here, which is changed to 6B0. So basically we just overflowed a little bit to corrupt just the adjacent chunk, and we just changed this size. And the thing is, we can check with our tool that the memory is still, the layout is still valid. And for the heap allocator, it's very important. Now, basically, what is important to know is that we're actually in the middle. By changing this size, we're actually saying to the heap allocator, this is all part of the same chunk, which is free, and this chunk are all part of the chunk. So now what happens is when this one is coalesced with the previous one, which is now free, it gives us a larger chunk. And this larger chunk ends up being basically all this chunk. And we can reallocate it and corrupt more data. So that's what we do. We know the size because we've used our tool to know the size. So we can allocate this exact size and take and exploit the designated victim scenario to basically replace the free chunk with an allocated chunk. Right. So in conclusion, for 64-bit, it's the same as 64-bit is the same as 32-bit for the old 64-bit. On your 64-bit, you have a different heap allocator that is used. If you look at and disassemble the actual line-up binary, you will realize that you have still this chain of wrappers, but at the end, they end up calling the libc malloc. So they don't call the mspace malloc anymore. They call an external malloc from glibc. And basically, to summarize, the default heap allocator on Cisco ASA for all 32-bit version and all 64-bit, they use dimalloc 283, and for the recent version, they use glibc. So it means now with glibc, they have safe unlinking, which prevents this kind of overflow, but they still don't have safe unlinking on the actual mempool metadata that is specific for Cisco. So basically, you can still corrupt data even though glibc has safe unlinking. So we actually need a library to parse ptmalloc2 chunks. So we actually did it. And we basically built 3 libs, which I showed you some parts. They are very similar to other libs that allow you to parse chunks in memory, like libtalloc from Aaron Adams or Shadow from argp, which is to parse jemalloc chunks. And the interesting thing is we've tested it on both dimalloc and ptmalloc and 32 and 64 bits. And we've used RedSync, which is a plugin to synchronize GDB and IDA-Pro to basically retrieve the symbols. So that's how we are able to show the name for the functions. And both tools actually support callback to actually deal with the mempool headers. So dimalloc will call into libmempool, and libptmalloc will call into libmempool. So libptmalloc, we built a fork from libheap developed by Cloudburst, because basically, even though his tool is pretty awesome, we wanted to basically have the same kind of commands for all our tool. For consistency, it's easier for us to have the same kind of commands. It speeds the process of using them. And we also needed to integrate with the Cisco header. So to summarize the security of Cisco ASA, old versions use dimalloc 2.8. They don't have safe unlinking on the dimalloc. They don't have safe unlinking on the mempool. And their footer is broken in that we can actually corrupt data and they don't check the footer. And on the more recent version, they use ptmalloc, which has safe unlinking, but still the mempool Cisco-specific data doesn't have safe unlinking, so we can still exploit that. And the good thing about Cisco as well is when we reverse engineer more versions in the more recent versions, they actually added ASLR and DEP, which wasn't supported before. So just to summarize, good tooling is usually synonym of success. Future work we want to achieve, we want to basically abstract things so our tool can be used in other debuggers. And we want to test on more targets, maybe on more Cisco devices, because we focused our research on Cisco ASAs. And we want to implement maybe other commands. For now, we just implemented the one we needed to actually achieve our goal to speed the process of developing exploits, but you can make it more powerful because we're gonna release it. We're gonna release these tools very soon. Thank you. If you have any question. Yeah? No? Thank you very much.
It's the 11 o'clock break now. Coffee sponsored by Newport, so our coffee sponsors, so just go have a chat with them if you can. Also, in every single track, there's a bin bag at the front, so trying to crowdsource clearing up rubbish or anything, so if you can just kind of throw stuff away to leave, that'd be really helpful. Cheers.
Good question for you. When you're going through on the memory allocations and you have to get them adjacent, at what point do they come adjacent? Is that...
Yeah, that's a good question. It's very empiric method. In practice, what you do is you try and just do more allocations if you need.
Yeah, so it's kind of, you run it for a period and see
Yeah. What I showed is basically after I already tried several times until I end up having this kind of adjacency.
Okay.
But it's a very good question. I mean, and it's very similar with what you would do on browser bugs, where you need to spray some kind of memory to fill all the holes. Mm-hmm. And at some point, you know you've achieved your goal, and usually you do a little bit more just to handle. But sometimes you don't have this capability because it's multi-threading. ptmalloc is a little bit more complicated because it's multi-threading. It's gonna allocate stuff in a less deterministic way. But in our case, it was deterministic. So we
You had to make use of that.
Sorry.
You had to then make use of it.
Yeah. So we managed to exploit this heap management determinism, but it's not always the case. But it's good to, that's the way to go. But it's good to confirm it's actually adjacent, just because you need this adjacency for exploit purpose. Yeah, but it's a good question. Yeah.
Thank you.